Let us finish this chapter by taking a look at validation. As said multiple times before, the validation of the model that we found is very important. We have to check if the model that we have now is generalizable, so that it performs well on unknown, unseen data points, and not just on the data set that we use to construct it. Where can we use validation? We can use it for comparing two models and selecting the optimal or the best model of those two. So suppose we have two models, we want to compare them. How can we validate them? So how can we see which one would be better than the other? We could do this visually, or we could try to do this visually. Visually means that we make a plot for the model predictions for both models, and then we compare them. However, if you have a data set, and you have two models, for example, this one which is just a little bit above, and this one which is just a little bit below, how will you select the best one? So it's very difficult to visually see which one is better. One is just a little above the observations, the other is just a little below the observations, but there is no clear interpretation of which one is better than the other. So visual interpretation becomes difficult, especially for long data sets. So if you have a lot of time points over which we have to look, then it becomes very difficult to see which model performs best over the entire range. If there is a lot of variation, or if we are not looking at time series, when there are high dimensional data sets, then it is also, well, basically it becomes impossible to draw if you have more than 3 dimensions of, so basically 2 dimensions for the parameters and 1 output dimension. Another option would be to look at scatter plots, a scatter plot of the predictions versus the measurements. So you look at what did I measure, what are the observations for the output that I measured, and what did I predict for the same time points, and normally they should be very close together. So if you plot them one to the other, you would expect that the scatter plot will be approximately the first bisector. Again here, how will you select between two models which both of them look pretty okay? So these are very subjective criteria, and so we need a more objective criterion. And one of those is Nash-Sutcliffe. So the Nash-Sutcliffe criterion is often used in hydrology and is based on the model efficiency. So model efficiency given by this formula, basically what it does is it checks whether my model performs better than just taking the average. So here it checks if the model predictions are better than taking the average. So we see the denominator has yi hat minus y bar. So here we look at what is the difference between the average and the predictions. On the other hand, the numerator has the predictions versus the observations. And so if we have no information, if we have no model, the best thing that we always can do is take the average. So that's the best thing we do to make a prediction if we have no other information. Now we constructed the model, and basically we want to see, is my model performing better than just taking the average, yes or no? And then you can also use this to compare models. So a model with a higher efficiency will perform better than a model with a lower efficiency. Clearly, efficiency varies between minus infinity and 1 because this term, it becomes 0 if there is perfect fit, and so 1 minus 0 is 1, and then the other one, if this is 0, becomes infinity, 1 minus infinity is minus infinity. So if we have E, so the efficiency equal to 1, it means that for all I, y hat I was equal to yi, and so our model is perfectly fitting the data. There's a perfect correspondence between the data and the model predictions. If it is between 0 and 1, my predictions will do better than my observed mean. If it is 0, it means that the numerator and the denominator are the same. So it doesn't really matter if I take the average or the predictions, the model. So they perform just as well. And if my E is smaller than 0, my model is even worse than just taking the mean. So we can just ignore the model. The most commonly used way of validating is, as I said before, using an independent data set. So either we have two data sets available, or we take a large data set and we split it, and then we calibrate the model on one part, and we validate it with the other part. So one thing here that is important is that validation set cannot contain new information. So the information contained in my validation set has to be the same information contained into the test set. So for your validation set, you cannot include new variables or use another measurement method which has a better precision or so, or anything of that kind. So the way you obtained both data sets has to be identical.